So thank you very much, Elisabetta, for the introduction, and thanks everyone for being here. So I'll be very happy to share with you these results, these recent results from the EHT about Sagittarius A star, together with Maria Felicia. And I like to start by saying that all the results we are going to show here, this is the not just a single man effort, but this is the results of a huge collaboration and a big collaboration effort. We are more than 300 people in this collaboration, and this is a recent picture we took in Granada for the summer collaboration meeting, and Maria Felicia and I, we are here. And so I start with these two images, which represents the main outcome of the collaboration efforts, and also represents the first two and only two available images of supermassive black hole shadows. So to the left is M87, the 6.5 billion mass solar masses black hole at the center of the galaxy M87. That is 15 million light years away from Earth. And to the right, there is Sagittarius A star. That is the supermassive black hole at the center of the Milky Way, with a mass of 4.1 solar masses and at a distance of 27,000 light years from Earth. So as you see to the right, in the case of M87, things were a bit easier, and you see how the source structure was pretty stable across a few observing days that the source was observed. While on the contrary, in the case of Sagittarius A star, what you see here, this is only for one single day, although we observed for multiple days, and things were much more complicated. And this is exactly what we are going to focus on today in this talk. So before these two images were released, we only had indirect evidences of the existence of supermassive black hole, like for instance, the high energy events or the presence of relativistic jets in some active galaxies, like is the case of M87, that could be explained only by assuming the presence of a supermassive an actively accreting supermassive black hole at the center of the host galaxy. And this is a beautiful multi-wavelength view of the jet that was produced from the multi-wavelength working group of M87. While in the case of Sagittarius A star, the most striking indirect evidence of the presence of a supermassive black hole was provided by tracking, the orbits of stars around the galactic center of the stars, and by taking a look at the orbits and the radial speeds. So a supermassive black hole with a mass of 4 million solar masses should have been there for explaining such results. The theoretical interpretation and simulations of supermassive black hole already started back into the 70s, trying to understand what is the trajectory of photons and matter around the black hole. And you see here to the top right, this is the very first computer simulation of a supermassive black hole, and you see how it emerged this clear and bright emission surrounding the central dark shadow, which, because of the lensing effect, this is larger than the size of the event horizon itself. So for doing this, we used the very long baseline interferometric technique, which so far is the technique that provided the highest resolution in astronomy in general, but this was not enough for being able to image, these two shadows. So the VLBI technique was really pushed to the limit for this reason, because mainly ultra high resolution was needed to resolve the two shadows, and this means taking this into different paths. For one side, we could go to shorter wavelengths to increase the resolution, but this is not an easy task, and this is why it was not done till now, because going to shorter wavelengths, that means having reduced the efficiency of the telescope. Observations are weather dependent, and then the atmospheric coherence could be as short as a second, and of course, the pointing errors could be huge due to the small beam size. On the other side, we could use, larger telescope aperture to get a higher resolution, or in the case of VLBI, to use longer and longer baseline. And what was done was to use, Earth-size baseline, just reaching the limit of the Earth diameter. Also, very high sensitivity was needed, and in this case, we used bigger dishes for millimeter VLBI, which again was quite challenging and wide bandwidth. And all this required the ad hoc development of new and advanced imaging and analysis algorithm technique, as well as computational technique. This is why to make a single image it took many years. Now, this is how VLBI works, just to make you understand some plots I'm going to show later. So an interferometer observes source, all the elements of the interferometers have the source at the same time, and these are synchronized by means of atomic clocks. And what an interferometer here measure is a complex of is a set of complex visibilities, which are the Fourier components of an image. And what you see here in the central plot, which is called UV coverage, each point in this plot represents the projected baseline distance, so the distance across pairs of telescope as seen from the source. And then as the Earth rotates, let me see if I can show this again. As the Earth rotates, as you can see, the projection changes, and we can assemble more and more frequencies here in this plot. This is called Earth rotation synthesis. And ideally, the more filled is this plot, the better is the way we can characterize the image with high fidelity. Because, you know, if we have a sparse sampling, this is the so-called Hill-Post problem. Actually, literally, an infinite number of possibility of images could really fit this data. And this is why, before selecting what is the final fiducial image, we really produced the millions of images before being pretty sure that this was the image fitting the data. So let's talk now about the observation. The Sagittarius A star was observed during 5 days in 2017, April 5, 6, 7, 10, and 11 at 1.3 millimeter, with this array of 8 telescopes spread around the world. The most sensitive antenna was ALMA. And let me note that ALMA didn't observe actually during 2 of the 5 days, which are April 5 and 10. And moreover, during April 11, there was an X-ray flare, so the source was not, quiescent. So in the end, we are left with these 2 days, which are April 6 and April 7. Here is the UV coverage, which are supposed to be the best days. And if we look carefully here, you see that April 7 actually has more data points in the UV coverage, because this is the only day where the 30-meter IRAM station also joined the observations. So in the end, it turned out that the best day to work with was this April 7, which has, the longest observing duration, the largest number of detection, the best UV coverage. So that's why you saw only the image for 1 day. This is the best day. And then the second best day is April 6. And we use this as a secondary validation dataset to make sure that what we get is consistent. And again, in this slide, so about this plot here to the bottom left, so this is the visibility amplitude, which represents the correlated flux density of the source versus the baseline length. And then you see 2 panels here, vertical, because these are the 2 days, April 6 and April 7. And then there are also 2 lines, because we are using 2 different calibration pipelines for the data. One is called HOPES, one is called CASA. And this is, of course, to have 2 independent tests to make sure that what we get is actually correct. And as you can see across pipelines and across days, these plots are absolutely consistent. And this gray line here represents a simple fit of a thin ring with a diameter of 50 microseconds, which is blurred with a beam of around 20-something microsecond, which is the nominal resolution of the EHT. And this is just to show how we can already play this trick here, and we already see that there is something that looks like a ring in this data. Before doing any imaging, before doing anything else, this is just already a clear indication from the visibility plot. And actually, Maria Felice is going to tell you more about this. So the case of Sagittarius A star was, as I mentioned at the beginning, very special and more complicated. This is one of the special treatments we did, which was essential for being able to disentangle the actual variability of Sagittarius A star from the variability induced from instrumental fluctuations. For this reason, we characterized the antenna gains by using 2 calibrators, which are this one, and Alpha 30 and J1924, which are 2 quite good calibrators because they are quite compact, bright, they are the flux density is fairly stable. And what we did was to characterize the antenna gains, so the station variations in these 2 calibrators independently. And here you see each plot here represents each antenna of the array, and the 2 colors represent the 2 different calibrators. You see how they are in very good agreement. And once we manage to get this, we then interpolate this to the Sagittarius A star timestamps and transfer this to the Sagittarius A star data. And so at this point, we are sure that if we see variability there, it's not due to instrumental effects, but this is the true variability, the intrinsic variability of Sagittarius A star. So that's a plot from one of the team I led, and this is in paper 2. And just to give you an idea, that looks like an ugly, simple plot there, but this is really the outcome of many, many months of work, because for each single calibrator, of course, we have different pipelines, we have different days, we have different imaging algorithms, we have different people making the images. And so we ended up by designing this kind of evaluation matrix that, of course, I don't want you to read these numbers, just to give you an idea. And that help us to, to select the final fiducial images. This is of one of the two calibrators. And once this is done, then we can obtain one single data point of the plot I showed before. And this was done in several rounds. Now, again, why is the case of Sagittarius A* was special with respect to M87? So this Sagittarius A* offered mainly two big challenges. One of these is the scattering effect produced by the turbulent ionized plasma in between us and the galactic center, which is producing mainly two effects. One is due to the diffraction, which produces an angular broadening of the image, so the image looks blurred, let's say. And the other effect is more stochastic and produces, which is done to the refraction, and produces this small stochastic substructure here in the image. This is why the image looks like this. On the other side, we have another, the other challenge was the one about time variability. So although Sagittarius A* looks, bigger than M87 in terms of apparent diameter in the sky, it is more than 1,000 times smaller and less massive, which means this also is reflected into the dynamic of scale. So if a light ray takes a few days or weeks to go around M87, in the case of Sagittarius A*, this is 1,000 times shorter, which it translates in terms of minutes. So, which means that while we are observing the source is continuously changing its shape on time scale of minutes. So how did we manage to tackle these two issues, and which approach we used to mitigate these two effects? So regarding the scattering, we could decompose the on-sky image into an angular broadened image, which is done to the diffraction, plus a residual stochastic component, which produces these refractive substructures. So in the case of the angular broadened image, what we did was to characterize the screen properties by using lower frequency observations. And then we were able, to invert the blurring kernel and apply this to our image and obtain the intrinsic image. Regarding the more stochastic component, this was modeled in terms of a statistical model and was taken into account in the data by inflating, the error budget. Regarding variability, we used mainly two approaches to tackle the issue here and to mitigate the effect. So one of these approaches is called a snapshot approach, which consisted in taking the whole data set, dividing it into small chunks of data over which the source is stable, and then image each of these small chunks independently, and then obtain at the end an average image of all these. This is called snapshot. That's why it's called snapshot. The other one is called full track approach, which instead consists into decomposing the image into a mean image and then a residual variable image. And in this case, what we did was to image the whole data set. That's why called full track, and produce an average image, and then model the residual variations against this average image. So now that we that I explained how we face these two challenges and how we managed to disentangle the intrinsic variability, we are now ready to make the image. And of course, this is something that is really the first image, so we have anything to compare with and say, okay, we're right. So for this reason, we didn't use a single method to do this. We used 4 independent and totally different methods to make sure that the result that we get is consistent and it's the right image that in the end is going to fit these abilities. So we used the classical inverse imaging method algorithm, the CLEAN, that this is the community standard being using since 5 decades to make VLBI images. And this assumes the source, approximate the source as a collection of point sources. And the flux density and position of these point sources is iteratively determined. On the other side, we have then the forward imaging methods. 2 of these are belongs to the family of regularized maximum likelihood methods. We have 2 of these methods. One is the EHT imaging, and the other one is called Smiley, and these two methods use different regularizers in the imaging process, and then they select the image that best fits, the objective function. Finally, we have a Bayesian, fully Bayesian method, which explores the full posterior of the images, and then this completes the set of all the of course, I don't give all the details here, but just to give a general idea, this completes all the sets of the models of the algorithm we use to make the images. And each one of these methods requires, of course, a set of initial conditions and of parameters combination. And before using this on the actual data, we trained these algorithms with synthetic data sets, just to make sure that they work properly, right? So we produced 8 different synthetic geometric models, either ring and non-ring, ring and non-ring shapes. So from the left to the right, we have a ring plus hotspot, crescent, simple disk, elliptical disk, a point source, a double, and a GMT model. These are not just random models, of course. These were done such that their properties match the one of the actual Sagittarius A star data. So here to the bottom, you see in black, this is the visibility amplitude versus UV distance that we showed earlier. In black is the one for Sagittarius A star, and in red is the one for each one of these models. And as you can see, by height, it's indistinguishable. So each one of these models properly fits the data and seems to be, very similar. And what we want to do with our algorithms is to train them such that they can distinguish among these very similar models the different models that are on top of that, since we know the ground truth. So how the whole process does work. So we have these synthetic models, which are these training models. We use then a set of parameter combinations for each one of the algorithms. When I mean a set, I say, when I say a set, I mean literally tens of millions of combinations of parameters. And then we produce the image with specific combination of parameters. And once we have the image, the reconstructed image that you see here to the top right, we want to make sure that this image are properly being reconstructed. And so to do this, of course, we can do it because we have the ground truth and we can see which combination of parameter properly and successfully reproduce the ground truth. So, and when a combination of parameters satisfy this condition, then we put this in this box here, which is, called the top set. So all the combinations of parameters that successfully reproduce the training movies, they end up in this top set parameters. And once we collect all the top sets, at this point, then we plug in the real data we have of Sagittarius A star, and we produce the images. To give an idea, this is a plot for one specific combination, just one of the combinations of the top set parameters. So to the top, there is the truth images of the different models, and then each line here represents a single software, VFMAP, EHT imaging, Smiley, and Themis. And you see how this specific combination of parameters successfully reproduces all the ground truths for the different geometric models. All right, as I mentioned, once we have all these top set, we are ready to plug in the Sagittarius A star data, and then we literally here produced millions of images for each one of this combination. And you see how all these images actually, they really show these ring-like structures. And the other good news is that in all of them, the size of the ring seems to be consistent. And then when we merge all these images that we obtain with the top set parameters, so you see this is the average image that we showed before. However, if we look to the single images, each one, we see that indeed, yes, there is a ring, size is okay, but some of them have some difference. For instance, brightness distribution in the azimuthal direction. For this, if we run a clustering analysis, what we find here is mainly 4 clusters in which we have slightly different azimuthal brightness distribution of the ring. And the one on top is just the average of everything, all right? The average of the average. So what this image is telling us, what all these results are telling us, is that there is a ring there. The size is pretty consistent across all the images. The only uncertainties we are left there is this azimuthal distribution of the brightness. And we are trying to make an image of something that is changing every few minutes. So this is absolutely fully understandable in the end. So we made the images. we show how we tackle all and mitigate all the weird effects that were expected. Now, at this point, we need to quantify the morphological properties of the image. And for doing this, we use the different approaches. Again, one of the messages that I want to give away here is that for every single thing, every single step we took, we always use multiple methods to validate and make sure that what we were getting was okay, was correct. So we are using two families of methods here. Some methods extract the features of the morphological features of the image directly on the image domain. These are called image domain feature extraction. The other family of methods extract this information directly from the visibilities. Let's focus now on the image domain feature extraction. In this case, we have, again, multiple methods, even in this family here. We have the non-parametric methods, where we extract the morphological information by performing this kind of ridgeline analysis on the image itself. And then we have a parametric methods in which we approximate the source in terms of a template, and then we play with the parameters of the template until we get a good fit, and then we extract the parameters. The other family of methods is the so-called geometrical modeling, in which we extract this kind of information directly from the visibilities. So this plot maybe looks a little bit confusing. I'll try to explain here. So we approximate the source here in terms of simple geometric models, and that are listed here in the x-axis. And you see, we both have ring and non-ring models here. The non-ring are indicated with a cross, the ring model are indicated with an actual circle. And the complexity of these geometric models is increasing, going from left to right. And what we have in the y-axis is the relative Bayesian evidence, which is just a way to indicate whether, to express whether there is a preference of one model over another one. And this top area here represents the highest evidence region. And this is just a zoom of this area here. And this is an amazing result, because an exploration of simple geometric models clearly demonstrates that the ring-like morphologies, if you see here, the vast majority of them are rings, provide a better fit to the Sagittarius A star data. So again, from a totally independent method, we again have another indication of the presence of a ring there. And this is from a totally independent method from the image domain feature extraction. And this is the final slide, and then I leave the floor to Maria Felicia. So we mentioned about the different imaging algorithms. We mentioned about the two different calibration pipelines. We mentioned about the different methods of feature extraction from the image domain, parametric, non-parametric, from the geometric model of the visibility. So when putting all this together, this is represented with different colors, and these are two relevant parameters. In the upper panel, we have the diameter. You see how this is amazingly consistent across all these different and independent methods, data sets, and algorithms. And we also have the two different days here in which we are making sure that this is correct. And to the bottom line, there is the ring width, which is found to be around 30 and 50% of the ring diameter indicated here in the bottom. And again, you see how this is in great and amazing agreement across all these different and independent models. All right, now we have the images, we have the properties, we have everything. So what is this telling us from a physical point of view, and what is the physical interpretation? For this, I leave now the floor to Maria Felicia, and she will continue the presentation.
Thanks, Rocco. So, as Rocco said, he just showed us how got the image and how confident we were on this result. Now, let's see what this image, there is a echo. I don't know if can you hear me?
Yeah.
Okay, I hear like an echo when I'm talking. I don't know why.
See, Maria Felicia, you have to switch off you have to mute yourself in Zoom.
No. Okay, fine. Can you hear me?
Yeah. Yes, we can. Yeah.
Okay. I was saying, no, just let's like see what the image tell us about a black hole and its near environment, no? And what we can learn about physics, no? And let me stress just one thing, no? Our goal, EHT goal, is not only to capture an image, but also to interpret it and understand, no, the physics of black hole and test also gravity. And as you know, Sagittarius can be studied in a way that are impossible for other sources, and making it just like a good laboratory for exploring many astrophysics phenomena. So now we want to understand first how does the accretion flow of this source, especially what happened to how Sagittarius works, no? We know that these flow are low luminosity, low density, and we have tried not to understand how the magnetic field behave and how the temperature of electrons and ions is working, no? And also everything concerning their geometry. So to extract all this information, no, what did we do, no? We assume, first of all, or we generate a huge suite of general relativistic magneto-hydrodynamics simulation. Let me stress general relativistic because we are using general relativity, Einstein equation. Magneto because is magnetized plasma. And also we have to consider, no, how the plasma move in this magnetic film and understand the hydrodynamic, no, and this means how the gas behave. So we have understand many things. So our main approach was to compare resolved EHT data at 230 gigahertz and unresolved non-EHT observation also from radio to X-ray wavelength to prediction from a library of model based on this SgR EHT simulation. And we included like a aligned, tilted, and stellar wind simulation. Radiative transfer was also performed. We included many things just to see if like our model is able like to fit the data. Please go ahead. Thanks. So as you saw before, we run a very large suite of this simulation, and we divided this simulation into sets. After we did some checking on size or on shape, geometry, temperature, and so on. And we followed just two main directions that depend on how the magnetic field is organized, no? And you can see that we have standard and normal evolution model from one side, where you can see that the magnetic field appear to be a little more disordered, no? And we have from the other side, magnetically arrested disk model, where the magnetic fields appear just like to be more ordered, with respect to the same part. With that, what we did, we changed the spin, we changed the inclination of the observer, we changed the temperature of the electron versus the ions, etc. And we tried to determine which of this model agreed with the data, which model passed and which model failed, to be sure about our simulation and later about our interpretation. Go ahead. So what we did in this huge library, we said, okay, what type of observation can we compare with these two, with sun and mud? Which of these pass and satisfy the observational constraint and which does not? So let's do the first test, first pass fail test, and we call it test 1, and we did this test on image size and structure. The first thing that we ask ourselves is, are we getting the right image size given the given mass and the spin, or we are missing something in terms of symmetry or in the image size? And how we do, or how we see, how we are able to see this, through this simulation and compare this simulation with data. So a passing simulation look like the left side, and if we look at the plot of the interferometric visibility amplitude in function of the baseline, this plot, yes, Rocco showed us before, it is possible not to have information, as we said, on the sides of the image, and also understand whether or not there is a ring or there is a red disk, and we don't see the brightness depression inside. And this plot tells us how much the flux there is in the entire images, And the one of the left, if you observe, show us like a regular, beautiful, nice ring, while in the other case, the image look like a very fine and very bright on the right side. So when we have an image like the other side, on the left, and we look like at different interferometric information, as also Rocco showed before, amplitude as a function of baseline, what we see a lot of amplitude at this long baseline. Then we have right amount of amplitude here in the second minimum, while in the other case we have nadir. And what tell us that the first case where we are seeing this beautiful ring is the case that is passing. The other case is not passing. Yes, thanks. Now, this plot seems like a little crazy, but to us was the way of synthesizing all of the information in one unique plot. And we have again sane versus mud. We have the observer inclination, 10, 30, 50. And 19 means that we see is the edge on, where we are looking at the accretion flow in this way, versus face on, where we are looking where we see the full ring, And also, as we go from the inner radii to the outer radii of this wedge, we can also see and understand electron temperature, increasing the radii correspond to decreasing electron temperature. So going from the left to the right, on the top, you can see also the spin of the black hole, and we have first counter-rotating large spin, zero spin in the middle, and co-rotating large spin, positive large spin on the other side. Why? What are the color? No, why is green, yellow, and red in this plot? We have made our model with code, let's say first, with code that like make various assumptions about the SgR EHT model. And so we want to be sure that our result does depend on how we have implemented the solution of those equations. So green means that however you implemented it, this model pass. Yellow means that some model pass, other model not, and red means that all the model fail. What do we learn from this image and structure? That red means it no go. So edge on with high spin inclination, especially positive spin cases, do not fit our data and not image size and structure. So we have clear these first results. Go ahead. Now we did another test that we call it again pass-fail test 2. And this test was a type of test was done on the whole spectrum of sources. As we mentioned, EHT observed at one particular wavelength. For now, we hope to extend them in the future. But that means that we are not able to have more other information about SgA star, no? Because we could have many other information. We have infrared information, X-ray information from many other observation. So whatever the model is, it should also obey at like the amount of flux, the amount of brightness the source generating their other wavelength. And if it is too much or it is like let's say too little, then we should rule it out the model. No, we say this. So if we look like MUD type magnetic field configuration versus same type magnetic field configuration, we just are able to see which pass and which fail. In this case, MUD pass and say is not passing. The electron presenting the magnetic field emits through two processes. No, we know this. We have synchrotron emission where they are like rotating around the magnetic field, and Bremsstrahlung emission, where the ions and electrons accelerate one in the presence of the other and giving rise like to X-ray emission. So the model on the left does well, as you can see. The peak is appearing a little bit farther, no, right? The peak in the same simulation, and in the same, the still is completely overproduced because it's a little cooler, and which means that the Bremsstrahlung is more effective. And what we have, and the synchrotron peaks look a little different in this case, as yes, Rocco, thanks that you are moving. Yes. So it files here, and then this is the upper limit from, we have the upper limit from X-ray, and this is the amount of like the X-ray that our model produces. So that model, we say this fails, while the other model was passing. This plot is important because by running this broadband spectrum test in our entire library, what we ended up learning, we learn an interesting thing, and this was the first time we are getting at this. So we were very excited for this result. No? We understood something about the temperature of the electron. What we are plotting here is effectively the temperature, not the gas pressure over the density. So if we look to at MAD model, we see that the curves are all higher for different spin with respect to the sun. You see there is a difference in the sun model by a factor of 5 to 10. So same model are cooler than MAD model, which means that they peak at smaller radio frequency and overproduce X-ray due to the thermal bremsstrahlung. So even though we have this sophisticated model, this is hard physics, and we have to understand how much heat the electron getting, how do they communicate with the ion in the flow, and we know that this is an unsolved problem in accretion physics and the plasma physics, and this is the first clue that made and saying could be distinguished, as well as the flow temperature could be distinguished because of how much they produce in different waveband, and this is very interesting. Was interesting to us to understand this. So what happened? How we are asking, how do our model do in this broadband spectrum constraint? And we see that MAD does too great for ER infrared constraint, while saying does too great for X-ray flux constraint. For the reason that we said, one is cooler than the other. So in one case, you are like overproducing in one or overproducing the other one. And
5 minutes, Maria Felicia.
Sorry?
5 minutes.
Okay, yeah. Oh, 5 minutes. Oh, okay. Let's move on. Okay. So we did other tests, and what at hand we saw that the model, especially MAD model, but even some say that we still have some problem, and we have to understand, especially the variability, because we treated the variability separately. We get the message that there is something something missing, in our simulation, and we need to complete and to understand, to do more other simulation to understand better how to control the variability. So next slide. This slide is also important because we understood also that we have low inclination and means that rotation axis is not aligned at all with the galaxy disk. And another important thing that what we found, we are consistent with what gravity found, about the position of the flare. Go next slide. I will try to summarize in just a few minutes. And the other goal not only was to understand how our model, SgRA EHT model, how the flow behave, was also to test black hole metric, and answer some question. Sorry?
No problem. Please go.
Okay. What we asked us, if we relax like the assumption that Sagittarius is a Kerr black hole, can we quantify this deviation or impose like some constraint on this alternative model? Another nice question, because many papers were written in the past about the fact that Sagittarius could not be like a black hole, but like a crazy exotic object. The second question was, is Sagittarius really described by a black hole space-time? And how all our measurement fit in the broader landscape of gravitational tests? Go ahead. What we did is, I will try to summarize, to quantify the deviation, we connected the predicted shadow size to an image diameter and compare it to the measured real diameter through this wonderful equation, where that means that we are able to measure dm is the ring diameter, the measured ring diameter that came from imaging and model fitting, then from data. And the het means the fact that we are working with a measured quantity, and that may differ from the true value, because of the measurement biases. So we have an important factor that is alpha, is the calibration factor. And this factor is defined as the ratio, as you can see, between the measured diameter of the image to that of the shadow, which can be used as a proxy for the shadow diameter. The calibration factor is determined by the physics of the image formation near the horizon, and quantify the degree to which the image diameter track that of the shadow for any underlying metric and for different realistic model of accretion plasma. So the shadow diameter depend on the metric and its property, like spin, potential charged, as well also on the observer inclination. Is a purely theoretical factor because depend on the theory. We have this delta parameter that is very important to us, and is the deviation parameter, and just measure the deviation between the inferred shadow diameter and the spatial black hole of a certain angular size, theta, where theta give us the M over D prior. And let me just stress one thing, or maybe you could ask later if you want. What I have to stress also now, here we wrote that we used in the equation just one calibration factor, but this calibration factor is a product of two important other calibration factor, because one came from ray traced image model, and the second one is the convolving of this model with observational effect. So we used all these relation to infer the posterior on the deviation parameter given the EHT measurement and prior information. The posterior were derived from the dynamical analysis of S2 star orbit by Keck and VLT. As you can see here, there is a discrepancy between the two values of about 4%, then we had to use both to be sure about our analysis, our calibration analysis. Go ahead. So what we have here, we calibrated the relation between the geometrical defined black hole shadow and the observed size of the ring-like image using a large library that include non-Kerr and Kerr simulation. And here what we have the fractional diameter difference between the diameter of peak emission that we have in images and that of its shadow obtained from 3 different types of simulation. No? And as you can see, the blue histogram showed the result of 180,000 snapshots from in time-dependent SgR EHT simulation in Kerr metric, changing like spin, inclination, and plasma parameter, while the orange show the same but for analytic plasma model in Kerr metric, and we relaxed some assumption on this SgR EHT model. And while the green histogram show the result of analytic plasma model in metric that deviate from Kerr. And also we used parameterization, parameterized metric, that does depend directly from a theory, but this parameterization are able to mimic many theories just using one equation. This is amazing. And what we saw that this distribution peak at a small positive value, and this indicates that the peak of a bright ring is slightly larger than the boundary of the black hole shadow. Next slide. We did the same, so we calibrate the relation for the reconstructed model. This means that now we are using alpha 2, the other, in the previous we used alpha 1 calibration factor. Here we are using the alpha 2. And we have the fractional diameter difference between the diameter of peak emission, but in ground truth images, and the dose of reconstructed through these 3 different imaging methods that also Rocco showed before. And what we see here also, that the small offset in the calibration parameter mimic those seen in the analysis of the actual data, and again we have the distribution peaks at small positive value. This is was wonderful.
I think I think we need to stop. I don't know if you are almost at the end of your slide.
Yes or not? Okay, I have just I can finish with yeah. Okay, don't worry.
Which one?
Do you have a summary slide, maybe?
This one?
Yeah, okay, yes. The point, what we take away about our all our result is the Sgr probe something that not was explored before. Then we added a new gravitational test. Contrary to the case of M87, we do not have any ambiguity about the mass, because the mass was also found by Keck and gravity. We had a precise mass. And we also we confirmed the SgR again. Then Einstein still is happy, now that his theory is still working. And another interesting fact is that despite we have different mass, the 2 black holes they have different masses, they follow the same, they are in agreement with SgR.
Thank you very much, Marita. Thank you also, Rocco, for a very comprehensive talk from the image reconstruction to the theory. So now it's time for the questions. Yes, Stefano?
About the top set parameters, the selection is done based on what? Some threshold in probability, and why